start with a question. Have you ever played a game where the rules keep changing? One day you're scoring points, and the next, the goalposts have moved, or the rules have flipped entirely. That right there is non-stationarity. The environment just won't stay put. In the world of reinforcement learning, this is a huge challenge. Non-stationary RL is about training systems to adapt when the rules, data, or goals keep shifting. And it's not just theory, it's all around us. Think of stock market trading, where trends and world events turn each day into a whole new game. Or picture warehouse robots navigating ever-changing layouts and obstacles. The paper we're exploring today tackles this head-on. It introduces Adam-Rel, an adaptive optimization method that helps RL agents stay grounded when things get messy. Think of it like a stability coach, recalibrating strategies on the fly to keep learning smooth and effective. Ready to see how this can reshape reinforcement learning? Let's dive in.
Hello and welcome. Let's kick things off by talking about why Adam, the popular optimizer from supervised learning, might struggle in reinforcement learning. Reinforcement learning, or RL, deals with data that shifts over time, also known as non-stationary data. Think of it like teaching a student whose lessons keep changing. Adam wasn't really designed for that. On this page, you'll see the author's main idea. Instead of piling on extra tricks like target networks or clipping updates, they modify Adam itself to better handle non-stationary data. They dive into how RL's constantly changing gradient magnitudes can throw Adam off. The goal? Tweak Adam so it stays stable and adapts when the RL task evolves. Now, still on the first page, check out how reinforcement learning is framed as teaching agents through experience. It's powerful, applicable to areas like autonomous driving, but it differs from supervised learning because everything keeps shifting. The data, the agent's behavior, even the value function is in flux. Researchers often use workarounds like target networks or other techniques just to keep everything from blowing up. But these add complexity, and some are not consistently documented. It's like patching holes in a boat without really fixing the underlying design. As you see here, it can lead to reproducibility problems, making it tough for others to replicate or compare outcomes. Moving on, this section on the next page focuses on tweaking Adam for RL's changing environment. You probably know that Adam merges two forms of momentum, one for the average of past gradients and one for their squares. And it uses exponential decay to downweight older gradients. But Adam assumes data doesn't drastically shift. In RL, policy changes can spark massive swings in gradients. That makes Adam's built-in normalization go a bit haywire, destabilizing training. The authors propose resetting the time component in Adam whenever there's a big shift. This way, the optimizer doesn't assume it's on the same steady track as before. By doing this, Adam can be more flexible and less prone to runaway updates. On this same page, there's a quick refresher on RL's core concepts. RL agents operate in a Markov decision process with states, actions, and rewards. It's different from supervised learning because here, the data distribution changes as the policy updates. Each time the agent shifts its strategy, the environment effectively changes. That's a big contrast from fixed datasets in supervised learning. The authors emphasize that this dynamic nature is crucial to understanding why standard optimization can behave unpredictably. Here, the authors dive deeper into where non-stationarity comes from. Notice the mention of bootstrapped value estimates, like in temporal difference learning, where the target depends on the agent's own shifting parameters. This can create sudden or gradual changes in the loss function. They hone in on abrupt changes, which can happen in methods like PPO. PPO updates the policy and value functions after each rollout, effectively switching the optimization objective. Even if each phase is stationary, jumping from one to another creates a bigger, overall non-stationary picture. So the paper treats these switches as separate, sequentially optimized tasks to explore how to keep Adam stable when the floor keeps shifting under it. Next, the authors outline various attempts to tackle non-stationarity. Ever heard of the gradient contamination hypothesis? It suggests that momentum estimates might actually work against the optimizer after a shift in the objective. Resetting momentum can help, so the paper also discusses that idea. Then there's proximal policy optimization, PPO, which uses a clipping approach to keep updates from spiraling out of control. You collect rollout data, break it down into mini batches, and iterate the updates. Momentum-based approaches come in handy here too, because they smooth updates over time. But if your momentum is based on stale or mismatched gradients, it can do more harm than good. Now on this page, the text zeroes in on momentum's importance. It's great for smoothing out noisy updates. Adam in particular uses momentum terms to keep updates within a safe range. But what happens when you suddenly hit a big gradient shift? Imagine training is going smoothly and then, bam, there's a giant jump in gradient magnitude. How does Adam react? The authors simulate exactly that scenario. They want to see how Adam's initialization and momentum terms cope with these abrupt jumps. It's like testing how a car handles a sudden turn, giving insights into where Adam might swerve or spin out. Here, the authors highlight an instability issue with Adam's momentum when gradients change unexpectedly. At the start of each new task, Adam's momentum is at 0. If the new gradients are large, Adam's scaling can initially overshoot, creating instability. So they propose Adam-Rel, Adam with relative time steps. Instead of carrying on as if it's one continuous training session, Adam-Rel resets its time step to 0 whenever we switch objectives. This keeps the momentum in check for the new gradient magnitude. Essentially, it applies a correction to avoid those huge spikes in update size. It's a straightforward fix that appears to reduce a lot of the problems that come with abrupt changes. On this next page, check out the graphs comparing how Adam and Adam-Rel behave when facing non-stationary gradients. Notice that Adam's update size often spikes big time, while Adam-Rel keeps it more even, thanks to that resetting mechanism. There's also some pseudocode showing how Adam, Adam-Rel, and a third version, Adam-Mister, differ in how they handle the momentum reset. Here, Adam-Mister is a variant of the Adam optimizer that fully resets its momentum-related parameters when the training objective changes. In other words, whenever there's a new sub-problem or a sudden shift in the environment, Adam-Mister discards all momentum built up from previous gradients and starts fresh. The main takeaway? By resetting time steps strategically, Adam-Rel avoids the big surges in update size. That can help the model learn more steadily, without overcorrecting every time something changes. Now the authors move from theory to practice. They test Adam-Rel on two RL algorithms, D, Q, N, and PPO. First, they use the Atari 10 inches benchmark for off-policy learning with DQN. They stack it up against standard Adam and Adam-Mister over 40 million frames. Then, they try it on PPO with Craftax Classic 1B and the full Atari 57 inches suite for on-policy scenarios. You'll see that they exclude two games, Montezuma's Revenge and Venture, because in those, most algorithms struggle. This way, they can focus on more meaningful comparisons. Keep an eye on how Adam-Rel handles these long training runs. These are big experiments, which really stress test the optimizer. Here, look at Figure 2. It shows how Adam-Rel stacks up to Adam and Adam-Mister on the Atari benchmarks. For the DQN Atari 10 inches results, Adam-Rel is hitting about 66% human normalized scores versus Adam's 29%. That's quite a jump. The authors point out that part of the reason is Adam-Rel keeps its momentum info through these abrupt changes, unlike Adam-Mister's approach, which discards it all. They also talk about how they measured update sizes and gradient norms in the Craftax Classic environment. It gives a closer look at how stable the updates are. Notice how Adam-Rel's updates stay more consistent. On this page, we see Adam-Rel's performance in on-policy tasks using Craftax 1B. The authors show that Adam-Mister, which completely resets the optimizer, underperforms Adam here. Adam-Rel, however, comes out on top in all metrics. Check out the geometric mean scoring they use for achievements like collecting diamonds or eating a plant. Adam-Rel does well even on tough tasks. The takeaway is that retaining some momentum information, rather than throwing it all away, helps the optimizer adapt, which is especially useful in these on-policy settings, where new data is constantly streaming in. Next, the focus shifts to the results on CRAFTA X1B and Atari 57. You'll see Adam-Rel outperforming Adam and Adam-Mister on CRAFTA X1B, scoring better on tasks like collecting diamonds. Then, with Atari 57, Adam-Rel wins in 33 out of the 55 games tested. Look at the charts. You'll see that Adam-Rel's improvements are especially noticeable in the higher scoring games. The authors highlight this as an example of how resetting the time step can pay off in complex, varied environments. This section circles back to the theory and relates it to what's observed in the experiments. Gradients spike when a new objective starts, about 29% for Adam and 45% for Adam-Rel. Interestingly, that spike is smaller than the models predicted. Also, these gradient increases don't remain high forever. They settle back down. That means even though we talk about abrupt changes, in practice, things tend to stabilize after the switch. Adam-Rel makes use of that by adjusting its updates in those early, high-variance moments. Now check out this comparison between experimental results and the paper's theoretical model. For Adam-Rel, you'll see that early drop in update size lines up well with predictions. There's not too much overshoot. But with Adam, there is an initial overshoot that recovers quickly, which doesn't match the model perfectly. The authors explain that their model assumes gradient magnitudes are constant, which they're not. Still, the general trend holds. Adam-Rel handles those abrupt changes more cleanly, avoiding dramatic overshoots. This page shifts to a broader discussion on optimizing under non-stationary conditions. The authors bring up loss of plasticity, a term for when a model becomes less adaptable over time. They mention techniques like resetting certain layers or adjusting the loss to keep the model flexible. Meta-reinforcement learning also comes up. That's where networks learn how to optimize themselves, potentially using metagradients. It's an interesting direction that could further automate or refine how we handle changing objectives. But the focus here remains on how to keep Adam stable when the ground is moving beneath it. On this page, they talk about various ways people have tried to enhance Adam in both supervised and reinforcement learning. Maybe you've heard of cyclical schedules or warm restarts. In RL specifically, there's a known issue called momentum contamination, where old gradients can mess up the new updates. Some methods suggest resetting Adam's state, but the author's approach is simpler. Just reset Adam's time step, not the entire momentum. This helps avoid contamination while still preserving useful historical gradient info. Especially in policy learning, they argue that keeping some momentum is actually beneficial, contradicting the idea that momentum should always be thrown out after a shift. The authors then touch on limitations. So far, the paper mostly looked at discrete, abrupt changes, like switching from one task or set of objectives to another. But real-world RL can involve more gradual, continuous shifts. They mention that future work could examine how to apply these resetting ideas in those scenarios. They also hint at broader uses for Adam-Rel in continual learning or synthetic data training. The question of how update sizes behave under non-stationarity is still open. If we can better understand that, we might discover even more robust optimization methods. Finally, we wrap up. The last page reiterates the core message. By resetting Adam's time step when big changes happen, we can handle non-stationarity better. The authors show that abrupt jumps in gradient magnitude can lead to instability, but Adam-Rel's simple approach deals with that effectively. Have tested Adam-Rel on both on-policy and off-policy RL tasks and found notable improvements over standard Adam and other variants. It's straightforward to implement too. So if you look at any of the RL tasks described here, you can drop Adam-Rel in place of Adam and potentially see more stable learning. That's where they conclude the paper, emphasizing the practicality of this method for tackling discrete shifts in RL objectives. To wrap up this deep dive, think of Adam-Rel as a handy toolkit for navigating those tricky, constantly shifting RL landscapes. Whether you're dealing with small tweaks or abrupt changes, having an optimizer that can reset at the right times could save you from a lot of training headaches. Thanks for following along, and feel free to revisit any of these sections if you want another look at the finer details.